Testing, testing. Welcome to, this is CS4510, L12, I think. Is that right? L12A. Godel, Incompleteness. He's German. It looks like Godel, but it's pronounced Godel, I guess. Incompleteness. So the following is perhaps the most important lecture, the most important theorem in the course. Everything else is just sort of baggage building up to this theorem. This theorem is like historically significant and very important, but it is also my favorite theorem because one of the reasons I got involved in this class was actually because of this theorem. It's like I had some Wikipedia understanding of this and there was nothing else. I couldn't find a course to teach it. So I ran around begging faculty, hey, can you do something with logic? Do we do anything with logic? Is there a logic course? And everyone was like, no, we only do geometry. We only know how to do geometry. So no one told me that before coming to Georgia Tech, I guess. But there was nothing that ever dealt with axiomatic set theory or logic in any way. So instead of, that's not true today. We have many faculty who do this. But at the time when I was an undergrad, this was not true. So instead of teaching me logic and things like this, I just taught it to myself. And then they just hired me to teach this to undergrads. So that's kind of how I got involved with this. So it's probably my favorite theorem for that reason. Let's talk about where we are in the course. We talked about Russell's paradox. If we're in a naive set theory, we have some form of an axiom of unrestricted comprehension. There exists a y for all x, such that x is an element of y if and only if phi of x, where phi of x is some well-formed formula. It is a predicate, right? And so basically this is set builder notation. You can construct a set, if you can construct a set over any well-formed formula, bad things happen. So Russell said, okay, we'll consider the set of all sets, consider the predicate to be, it is false that the set contains itself. And then we may apply unrestricted comprehension to assert that there exists some set y, such that for every x with x and y, that is true if and only if it is false that x contains itself. Now, we may consider by specification the case that y is equal to x, which is what we're really asking is, when we ask if y equals s, we're asking, does the set of all sets that do not contain themselves contain itself? So when we perform such a specification, we get that y is an element of y, if and only if it is false that y is an element of y, right? And therefore we have derived that true is equal to not true, and throw away the whole system, right? And in fact, this works, this kind of a little attack works against any system, any axiomatic system that has anything analogous to a principle of unrestricted comprehension, right? So this Frege came up with the system. It was a great first system because it tried to take the basic ideas of syllogism and logic and thought, and convert it into a logic. But we found that there's kind of a bug in it. It's not very good. So we need to fix this. Some people took this as evidence that like logic is bad. What was it? Logic is barren, so don't look at it. But other people wanted to repair this and thought that maybe a more fine-grained notion of comprehension could be used to construct something like this. So the first idea is like, while unrestricted comprehension could be considered something like set builder notation, fine, use something called restricted comprehension, which instead of defining just any sets to be satisfying any arbitrary condition, only allow yourself to construct subsets of already predetermined sets. Okay? Where Z is something that's already been existed. And this is called restricted comprehension. It's much closer to an axiom that we have today of Z of C. Right. That mostly, just like on the surface, immediately appears to prevent the construction of with such a predicate like this. Even though this is syntactically valid, and it is definitely a well-formed predicate, doesn't work anymore, right? And in fact, there's more general problems in a more refined view of set theory, not naive set theory, but a more refined set theory of a set containing itself. Such a thing can be proven not to occur. Fine. Russell went a slightly different direction though. And he saw the core issue here is not reference, but self-reference, right? These kinds of attacks, diagonalization, are simply encodings of the English paradoxical sentence that says something along the lines like, this sentence is false, right? or I am lying to you, or many other such variants, right? So the problem of this paradox is simply the logical version of such of a sentence, right? Which is still syntactically valid or whatever, but it may not be assigned a truth. That's not good. The problem here is the this part. Nothing else is necessarily incorrect in the sense that one sentence may refer to the truth of another. It's the fact that a sentence may refer to its own truth. So what Russell does, he constructs something called the theory of types. And he assigns to each object a type, and he declares that each object of type I may only reference objects of type strictly less than I. So this could reference this one, or this one, or this one, and so on, right? So type I only references type strictly less than I, right? That immediately prevents any statement of type. Every statement has a type, so it immediately prevents a statement referencing itself because it also cannot reference any statement of type I, including itself. So this immediately appears to prevent self-reference. But as we'll see, not really. So Russell constructed the sentence of the form, I am not true, right? The theory of types is this long-winded, incredibly boring 3-volume work, which is, it took Russell and Whitehead is his colleague, it took them 12 years to construct 3,000 pages, and these guys are both logicians, so the symbols in this is completely, it's purely symbolic. There's very little English sentences to explain what's going on. The first volume and to some extent the second volume are all basic constructions of the naturals and so on. The third volume, they try to construct definitions of continuous functions and things like this. And there is some, it's very, very difficult to do that on pure logic, as you can imagine. That's something very, very advanced. You have to define the reals, you have to define properties of continuity, it's a disaster. But that's what the third volume attempts to do. And each theorem in the book is a pure sequence of symbols with references to prior symbols and so on, right? I thought about buying it on Amazon just so I could show you how big it is. It's like this thick, but I was like, I'm never gonna read it. And in fact, only 5 people in the world have ever read Principia Mathematica. It's not worth looking at. So they even had some trouble publishing it, as we'll see. But they tried to construct a basis for all mathematics. And they appear to prevent construction of sentences like this using this very complex system. But Godel, who was a young guy, he came along and showed actually this can still construct a sentence of the form, I am not provable. So what he does is he splits a hair between the notion of truth and the notion of provability. And although Russell appears to prevent discussion about truth, Godel uses a discussion about provability. Now, you can, not only that, he argues you can never prevent discussion about provability, no matter how much you prevent discussion about truth, which is the argument we'll present today. By the way, if something is provable, you may just assume it's true, right? So, this is a property, it's called soundness. Anything usable has to have such a property, any logical system. Trivially so, right? The truth of the statement is demonstrated by the proof. So if it's provable, it's true. Now this is, as we'll show today, not an if and only if, in fact. These two do not perfectly correspond. Are there questions so far? Right, so Russell and Whitehead, actually quick recap. What is the difference between a predicate and a proposition? This is a quick 2050 review. Let's suppose you have a predicate of the form, or the natural something like this, right? A predicate is just a propositional function in the sense that it's not assigned a truth value until it has no free variables. In any logical system, every proposition must be assigned a truth value. And this is not assignable a truth value until one of two things happens to its quantifier, its free variable. You either need to quantify over it, so this may be assigned a truth value. There exists n, such that phi of n. That can be assigned a truth value, right? The quantifier binds itself to the free variable, so now this is either true or false. It has no other free variables. You can also evaluate. That's the only two things to do. Both of those can be assigned a truth value, and these are propositions. Well, this is a predicate, right? So predicates can convert themselves into propositions, right? Upon either evaluation or binding. We seek two important properties. They spend 3,000 pages defining Principia Mathematica, and they hoped it would satisfy two things. First is completeness. And informally, completeness asserts that things are true if and only if they are provable. In the sense that if something is true, it ought to have a proof from it. Completeness is in the sense of like a basis of a vector space spanning everything, right? Your system is good because anything that happens to be true can be proven by such a system. You're not working with some strictly smaller system. In the sense, like, we know that, for example, a theory of numbers is weaker than a theory of sets, because you can build number theory from set theory, but perhaps not vice versa, and so on, right? So is your theory as general as possible? If anything is true, can it be derived from it? This is what they, not only did they hope that the system was complete, they hoped that the system was provably complete, right? Another way to say this is like, for F, any well-formed formula just means it is like grammatically correct over whatever the formal language is of the system. For example, it has to be some sequence of symbols like this. If it's allowed to be written down and it has no free variables, then either Principia Mathematica proves, and this symbol again means proves, not necessarily true, proves F, or Principia Mathematica proves the negation of F, right? So everything that has no free variables must be able to be proven true or must be able to be proven false, right? So this is the notion of completeness. The next one is of consistency. Consistency is, the last time we argued that truth cannot exist in contradiction, and that everything that can be, everything is either true or false, and there's not both and not neither, right? So what we would say is that, how should I say this? For any F, F and negation of F is always false, right? A system ought to be consistent, really more than it ought to be complete. If a system is consistent, that's like the bare minimum we need for a system to be usable. Completeness is also desirable because we're looking for a foundation for all of mathematics. We're trying to derive everything, geometry, number theory, calculus, all of this from a strong logical basis, you know. You're trying to build that on top of something that you know is good. That's why you want completeness. Consistency is the bare minimum required for any system to be usable. Yeah, I mean, like, if you don't have consistency, we mentioned before, if there exists even a single, by the principle of explosion, if there exists a single statement which is both true and false simultaneously, then the entire notion of truth is destroyed. Now, this is what they sought. Not only these two properties to be true for Principia Mathematica, but for them to be provably true. And once they could prove that Principia Mathematica was both consistent and complete, they could finish their life's work and then just, you know, put it on a shelf somewhere. But then Godel came along, and actually the story goes something like this. Hilbert was an old guy at this point. I think he was in his 70s, and he gave some retirement speech, and he gave this famous quote, "We can know, we must know, or we will know," something like this. And he basically said, you know, the logicians are going to win. We will find such a proof. We will be able to prove something to happen. Godel, I think, was 20, and he had, on like the third day of this conference, at a little round table, he ended up giving his first theorem. Any axiomatic system capable of sufficient arithmetic cannot be both consistent and complete. So what Godel proves in this little corner is that any axiomatic system capable of sufficient arithmetic cannot be both consistent and complete. So it can't be both. If it's one, it's not the other. Or maybe it's neither. Now, basically what he proves here is that Russell and Whitehead sought something that was impossible. You know, and this is actually kind of a common thing. If you fail to prove something 12 years or whatever, maybe try proving the opposite. Try the negation of such a statement and it might be easier to prove. And in fact, that's basically what Godel did. He didn't seek to prove that Principia, he didn't set out to try to show Principia was wrong, but he just noted, he was able to note that you could, although discussion about truth could be prevented through some complicated system, or at least on the surface, you could never prevent discussion about provability. And he uses that to shim into the system this great theorem. First, what is this notion of sufficient arithmetic? So there are consistent and complete systems that are toy. The empty system is definitely consistent and complete because there's no theorems in it. So I mean a QED. So you can always make like a weak system that's consistent and complete. But how much arithmetic do you need? Suppose you have the naturals under the relations of equality and just addition, okay? This is called Pressburger arithmetic. You can construct statements like for all A, there exists B, for all C, such that A, 3A plus B is equal to C, okay? That's an example of a statement over such a system. It has those relations, okay? And why do you do 3A? Because that's A plus A plus A, right? So you can, this is a well-formed formula over such a logical system. Turns out this is consistent in the sense that if you were given a statement of this form, you could always determine if it's true or false. Undeniably so. So such a theory is called decidable. In fact, there's a modern proof of Pressburger arithmetic using DFAs. So in fact, you could prove that you could always determine the truth value of such a statement using DFAs. So this kind of logical system is consistent and complete. Now, what if you had the theory of numbers with equality and just multiplication? This is called Pressburger arithmetic. This is called Skolem arithmetic. It turns out that it's true for both of these, that you could be consistent and complete. So these are small systems that are both consistent and complete, and these are not sufficient arithmetic. But it turns out that if you have addition and multiplication, then that's sufficient for you that satisfies, it turns out, sufficient arithmetic, quote unquote, and then that cannot be consistent and complete. Now this should surprise you. What's kind of strange about this? Is there an obvious comment? Yeah.
If you combine the two that are consistent and complete, it should be, the product should also be consistent and complete.
So that's kind of interesting because you could define a statement in here which could not be in either here or here. For example, for all A exists B, for all C such that AC equals B, AC plus B equals 0, let's say. That is a combination of additions and multiplications. So these are only multiplications and then only additions, but then you can construct sums with both. I guess the other comment I was going to ask is, most people consider multiplication to be just addition n times. So why is this not this? Or sorry, why is this one not this one? And the answer is, the difference is how do you define logically do this n times? That is, and in fact it is, to logicians, a fallacy, although computationally it's totally fine, that addition is repeated multiplication, because multiplication is a totally separate thing logically. It's like the difference between and or, right? So if you have both, it turns out that's too much. And then people have also studied, like, in a bounded sense, what is, like, let's say you had a bounded form of addition and multiplication. Are you still consistent? Can you still derive Godel's incompleteness term? And the answer is yes. Now, we're not going to focus on that too much, because any system that, I mean, this is such a bare minimum criterion. Any system that ought to be logically, like useful, like Principia is sought to be, should have multiplication and addition, right? Like, that's like such a simple bare minimum thing, you need those. I mean, like, fine, there are toy systems, who cares? We're looking for large, consistent, complete, strong systems, right? Questions on that? So the first problem is this theory of types is not good. So it prevents discussion about objects that we need discussion about, right? In the sense that we want to discuss objects of the language using the language. So what we need to first do is shim discussion of objects about the language into the language. Okay. So essentially, and this is part of the beauty of Godel's proof, and there's actually 3 proofs we can do of Godel's incompleteness theorem. This is the first one. He basically does not know what a computer is. He doesn't know what a string is, but this is like kind of analogous to a cybersecurity hack. He like has to invent a programming language without knowing what a computer is in order to hack it. So it's a very strange argument, but he uses the formal symbols of the well-formed formulas of whatever logical system we're in, let's suppose it's Principia, to construct such a contradiction, as we'll see. So we do something called Godel numberings. A Godel numbering is simply a function that takes as input a string and outputs a natural number, such that, according to the following way, suppose we have the following symbols of our formal language. What are the allowed symbols? Well, 0 is an allowed symbol. The successor is an allowed symbol. The negation, or the universal quantifier, the open parenthesis, and then the closed parenthesis, right? Now, this is not, I mean, obviously when you're working in logic, don't you need more symbols? Why don't you need the and? Yeah.
You can form the and from the not and the or.
Exactly, the Morgans, right? Well, you don't need the exist because you have a not and an for all. So just any symbol, anything useful could be rewritten in these ways, right? To each of these you assign an odd number, 1, 3, 5, 7, 9, 11, 13, okay? Now there are other symbols that are required, which are propositional variables, x, y, or pq, right? And to each of these you assign a prime number greater than 13. So these will be 17, 19, 21, 23, right, and so on. Whatever these are. So first we make a sort of lookup table like this. And then if we say if f is a well-formed formula, where f is equal to f1 to fk, where this is a string, then we let the Godel numbering of f be equal to the product of I equals 1 to k of pi to the lookup table's symbol of f of I. So all this really does is, given a string, it converts it to a number in a kind of a funny way. So for example, suppose we were considering the Godel numbering of, what is it? For all x, let me double check I got this. Yes. For all x, x or negation of x. Okay? This is going to be Godel numbered into what? For all is going to be 9, so we're going to have 2 to the 9. X is going to be 17, so we're going to have 3 to the 17. 5, open parentheses, is going to be 11. 7, and then x again is going to be 17. Wait, so look at this goes 11. Or is going to be 7. Was 13. This is a not, so this is a 5. 15, 17, 19, 23, let's try there. So, wait, what was this one again? This was a not, so this is going to be a 17 is going to be to the 17, is this right? Yeah. 19 will be to the closed parenthesis, which is 13. Okay, don't need that one. So this is some numbering, right? Now, here's the important part. First off, why is this numbering injective? Yes?
You can always map the left to something on the right.
Correct, but why is it false that two things on the left can map to one thing on the right?
Because they're prime numbers.
Prime factorizations are unique. So injectivity, we may say that let gamma of x equal gamma of y, okay? If these two symbols map to the same number, by the fact that it's called the fundamental theorem of arithmetic, by the fact that every number has a unique prime factorization, we know that x and y must be symbol for symbol, identical in length and character. So in fact, this implies that x equals y, right? And that's just the definition of an injectivity. So here's the thing, theory of types prevents discussion of x comma y, fine. Discuss the numbering of x and the numbering of y. So you can prevent discussion about objects, fine. You cannot prevent discussion about numberings because those are just natural numbers, right? That's kind of the first part of the hack, okay? We don't have to discuss references to other objects. We can just discuss references to numbers that happen to be numberings of objects. So rather than discuss the objects, we discuss the numbering of the objects, right? This is not something, this is like an old school thing because like today we know everything can be encoded as a string. So he doesn't know what a computer is, he doesn't know what a string is. So first he's got to talk about objects in some way. So he represents them syntactically, these syntactic objects as numbers. That's the first thing. The second thing is that properties of number theoretic properties can tell you a lot about an object, right? For example, let's say 2 to the 5 divides into some gamma of n, and 3 to the 5 divides into some gamma of n, and 2 to the 6 does not divide into gamma of n, and 3 to the 6 does not divide into gamma of n. What do you know about gamma of n? Or n? Let's just say n. Yes?
Could be represented by some multiple of 2 to the 5 and 3 to the 5.
The numbering contains as a prime factor 2 to the 5, but does not contain 2 to the 6. So forget the 3 part for a second. If something is divisible by 2 to the 5 and not 2 to the 6, consider the unique prime factorization of this number. What do you know about its object, according to the Godel numbering?
Contains a knot.
Correct. The first symbol is a knot. Okay? What do you know about this then?
Three to 5 is a factorization.
Yeah. What this basically says is the largest prime factor of this is 5. So 6 and above do not divide into it. So the largest prime factor is 5. So same here. The first symbol, this says the first symbol is a knot. This says the second symbol is a knot. So this looks like this. So if you know, for example, these 4 things happen to be true, then you know that the statement begins with a double negation. So what that means is you can convert gamma of n to some gamma of n prime by dividing out by the powers of 2 and then like shifting all the primes over, right? Get rid of this and then like shift these over. So you can manipulate the number in a way that allows you to apply axioms. Because what are the axioms? The laws of thought, the rules of deduction are simply syntactic transformations over the formula. So if these happen to be true, you can apply number theoretic properties, division, multiplication, and so on, to apply an axiom in some sense. But you don't really apply it to the object, you apply it to the number. Now, it's a little cumbersome to explain how do you take a number and you So I guess first you would do you would take n, just give me gamma of n, and then you would divide it by 2 to the 5, 3 to the 5, and then you would have to do something else to shift the numbers over. But that would be the first step, right? But anyway, the point is, yes?
So wouldn't 2 to the 6 and 3 to the 6 never be possible anyway?
What this, all this says is that like the largest factor is 5. So there, for example, it is not the case that it is 9. But if we only had this one, it could be the case that it was a 9 or a 11 or 13, right?
Okay, I think, okay.
Yeah, we'll do a quick refresh on some of the number theory stuff. Okay, so what Godel does now is the hack. He constructs 46 formula to hack this system. The first one is this relation. What is the definition of A divides B, by the way? Does anyone remember? We all know how it works, but does anyone remember the formal definition? I'll remind you, it exists some C such that AC equals B. That's all it is. There exists some number C such that AC equals B. That's what it means for A to divide B, right? And again, this is a relation, so it's either true or false. Then he defines, well, we did this one last time, but a number to be prime, and this is a predicate, so it returns true or false. It doesn't return anything, but it's either true or false. For any x, where we said, what was it? X exceeds 1, and, all right here. There does not exist a z such that z is less than or equal, less than or equal to x, and it is false that z equals 1, and it is false that z is equal to x, and z divides x. All right. I'm running out of space. No, that's perfect. Okay, so like this is a predicate that's just the definition of the prime numbers, right? The only numbers that satisfy such a predicate are those that are prime. They don't have divisors less than themselves, that are not 1 in itself, right? Okay, you can also construct a predicate inductively for this to be the nth prime number. Okay, that one's a little complicated, so we'll skip it. We're on like formula 3 of 46. Then he does, I'm going to give you one and I want you to tell me what it says. Let GL, something in German, of n comma x be such that there exists a y with y less than or equal to x, and x divides the nth prime of n to the y and x does not, it is false that x divides prime of n to the y plus 1. What y is this true for? It's a kind of complicated, there's lots of symbols. But importantly, he's doing this in the formal system, right? I'll give you the hint. N here is some number. Prime of n is the nth prime number. So if you think of the string like an array, the nth prime number is really the nth symbol of this string. And if x divides into y, but not into y plus 1, that really means that the y here that this exists for is the largest prime power of the nth prime number. So if x is the string and n is a number, what he's really asking for is like x is equal to, where we have the nth prime number here of y. So y is the nth, the y is the power there. So what it really means is y is whatever is at symbol n. So what he does is here is this is an array access mechanism. He doesn't have an array, he doesn't know what an array is. These guys only know what numbers are. They only know sets. They don't know anything except what they're talking about. So he has to basically invent an array access mechanism. He wants the ith character of a symbol. He has to define it somehow. So he constructs such a definition, right? I'll give you one more. Let L of x be, there exists a y such that y is less than or equal to x, and GL of y plus 1, comma x is equal to 0. Yes.
When you say GL is equal to 0, do you mean that it's false or that?
Yes, so like, it is not just predicates that return true or false, where a predicate is a relation or a truth function, right? There are also just functions that they don't return anything but just are a number. For example, P of n is the nth prime number. You can define this inductively, and it's not true or false. This one is true or false, whether or not the number is prime. This one is just the nth prime number. So here, G of L, there is no return mechanism, right? But let's suppose the return mechanism was the smallest y for this to be true. So I guess what we're saying is the smallest y that this is true for is 0. Yes?
So is there no smaller prime number, no smaller prime number in the string x?
Yeah, I mean, like, so y plus 1 of x would be like the y plus 1th prime number of x is 0. So what that means is the smallest prime that this is true for basically means that this term has a 0 in the coefficient of that prime number. So like p of y plus 1 is 0 in the exponent. But the smallest that this is true for is if this is p of y, whatever that is not 0. Whatever, we don't know what it is, but it's not 0 if this is the smallest one. This is the length, right? Anything else here, this is also equal to 23 to the 0, right? So if that's not 0 and that is, that's just the number of prime divisors of it, which is just the length. So in fact, this is a function that computes the length of it. He proceeds in a very, very complicated way of deriving. We're not going to go through all the formulas. I'll show you how difficult and tedious the construction is, but he basically invents a programming language. He invents basic operations of concatenation of objects, negations, the axioms he encodes into numberings. He does all of this, and what we really care about is the following two relations. He defines this relation, let x demonstrate y, and this to mean that x is a demonstration of y. So this should be true if whatever x and y are numbers, but whatever they were mapped from is a proof of y. So this is the kind of the important relation. This is the one he defines last. Now, how does this actually work? He says that the x is a number. So here's what an easy way to say it is that x is a proof of y. But what actually is going on is he says whatever x is a numbering of happens to be a proof of whatever y is a numbering of. But these are numbers. This is an operation on numbers using number theoretic properties, prime numbers, divisors, and so on. And he's able to construct such a relation and define such a relation. It takes 46 subformulas. There's like 46 helper functions to get to here. But this is able to be defined, and this is correct to define. Now, this is the part where we insert discussion about provability into any axiomatic system, right? We do need, all the relations require addition and multiplication, it turns out. So that's kind of where the sufficient arithmetic comes in. This relation is just, if you were to unfold the 46 subformula, for example, L of x is defined with GL of x and so on, right? So the formulas build upon each other. If we were to unroll it, this would be a nasty and ugly relation, but it would just be addition and multiplication and quantification all the way down. So it's definable. The way it actually works, just to give you a high-level programming thing, is that you first check that x itself is a proof. Or excuse me, the inverse of x here is a proof. The way you do that is check that it's a sequence of lines. Each line is either an axiom or an application of one of the laws of thought, which are themselves axioms, from the previous two lines. Okay? So that you first just do that syntactically to check that it's a proof. You can always just syntactically check something as a proof. That's fine. Then, to check if it's a proof of y, all you do is just check if the last line is equal to y. If the last line is y, then the proof deduces y. That's all it is. So there is no meta discussion necessary about proof validation, because this can be very easily mechanized. You can, given a proof, you can always determine if it's correct. The question, that's not the important question. The question is, how do you determine the proof? That's a different question than, given the proof, is it correct? You can always do this, verify a proof, but finding the proof is hard. So all he says is there exists a proof of it, that x proves y. That's what this is, right? And this can be true or false for any such numbers x and y, right? As long as they're valid encodings. And if they're not valid encodings, just suppose something happens, they return false, right? On the way there, this is like formula 43 or 46. He also defines, I think it's 21 or 22, this function sub of x, y, x, v, and y. So what this does is where v appears as a free variable in x replace with y in a substring sense. Substitution here is basically evaluation, right? Recall we have a function, and let's suppose we're not working in logic, but just like normal polynomials or something. We say f of x is equal to x squared plus x plus 1. When you evaluate this at 3, what you're really doing is a substring replacement. F of 3 is equal to 3 squared plus 3 plus 1. You literally replace the symbol x with the symbol 3. Now you could also do this for f of g of x, right? It's fine. And what happens here is that y would be the symbols representing the encoding of g of x. And then you would do some axioms to simplify and move terms around and whatever, it's fine. A plus b equals b plus a and so on. That can be done through the axioms, but the evaluation is just done syntactically. You literally replace the symbol with the sequence of symbols. So anytime v appears as a free variable in x, and of course these are all numberings, just evaluate it, so to speak. You substitute it in a very syntactic string replacement form, right? Are there any questions so far? Okay. So now let's proceed with the main proof. Consider the following predicate. F of x, so it has a free variable, to mean that there does not exist a p such that p demonstrates if you were to take x, every time there appears a 17, you replace that with x. Okay, nothing problematic. We can define such a predicate. There's no controversy yet. Why do we define such a predicate? We'll see. It's contrived, right? F is a predicate like any other. So simply consider its numbering. This is some number. This is a predicate. This is just some number, right? Plug and chug. What happens if we evaluate the predicate at the number which happens to correspond to its encoding, its numbering? So we evaluate the function essentially at its own code. Does not exist p such that p demonstrates, substitute, every time we see gamma of f, 17 in that, replace that with gamma of f. I hope that's the right number of parentheses. Nope. Yeah, here we go. Okay, it's getting more complicated. Let's simplify. This part, we're going to simplify first, and then see if we can plug it back into the original equation, okay? So what does this mean? Substitute, as we said, takes x vy, right? And every time v appears as a free variable in x, replace that with y, right? So this is an operation on the number, but it's really implicitly an operation on f, not the numbering of f. We just use this f as a shim, as the numbering is a shim, right? So we're really operating upon whatever this happens to be. Wherever 17 appears in that, we should replace it with this number. Whatever that number is, which happens to be its own numbering, we're going to replace it there, right? So again, notice the difference here between x, 17, and x. These are actually three different things, completely different things. 17 is the numbering for x. X is a number to be evaluated at. And x is also a number that is substituted in. So in some sense, there's an interplay here between a semantic and syntactic notion, where x is an object to be substituted in and also an object to be evaluated at. It's evaluated at in a semantic way, but it's substituted in a syntactic way. There's this interplay here. If we expand this, let me just write down f, and every time we see a 17 appear, we're going to replace that with gamma of f. So let's just write down f first. We have it here. There does not exist p such that p demonstrates sub x 17 x. Okay? Now, we're going to take every instance of 17 and replace it with gamma of f. There's a 17, and there's a 17. In a syntactic way, once we perform this evaluation, we get p demonstrates sub gamma of f, 17, gamma of f. Yeah, one more, okay. Something curious about this formula. Yeah.
Looks recursive.
Yeah, but how so? What's the recursion?
If you replace x with itself, when does it stop?
That actually that's important to define. It's not, there's two objects that happen to be the same thing, and that's kind of where we get to split the hair. And that's also why we don't get an infinite loop sort of thing. The theory of types can prevent an immediate discussion about an object with itself. But here, there are two distinct x's in some sense. So a semantic one and a syntactic one. Now they're just numbers, but that's okay. The answer I'm looking for is symbol by symbol. This line is identical to this line, right? So what we did was, we took a sub-formula, we took part of the thing, we tried to simplify it, we ended up getting back the original formula. So you took part of the formula, you plug it in, but then you get back the original formula. So this was just this. If you were to take f and evaluate it at gamma of f. And if you think about it, that's really what the substitution operation does. So these are the same. So we get that f of gamma of f is equal to there does not exist p such that p demonstrates. Now instead of this thing, we know it's this. That's on the left and on the right. Although the theory of types can prevent that discussion, no it can't because we shimmed it in. Now this is complicated. Let's simplify. Let this just be called G. Then this asserts that G is equal to there does not exist P such that P demonstrates G. Right? These two relations can combine together to perform a shim. You are not allowed to define something in the theory of types that references itself, yet here we have constructed a sentence that references itself. G asserts what? In English, what does G say? G says there does not exist P such that P demonstrates G. So in English, yeah.
There's no proof to G?
Yes. But who says it?
G.
Yes. So what is G saying in English?
G's saying that can't prove itself? Or is that too basic?
Well, it's not who's proving it, I suppose, but there is no proof of me. I am not provable. That is how we construct the sentence, I am not provable, even though we can prevent a discussion about truth. Now, importantly, this is, the theory of types we didn't get into. The theory of types does appear to prevent discussion about truth. If you can discuss numbers, you do a very complicated argument, and then you can prevent discussion about truth, fine. You can never prevent a discussion about provability, right? Let's finish the proof. G is either two things. We know two things about G. First off, G has no free variables, right? Since, I'll write it this way. Assume to the contrary that Principia Mathematica is both consistent and complete. Since G has no free variables, G is true or false. Okay? Case one, G is true. If G is true, we know that G, whatever says G says must also be true. So G says there is not a proof of G. So if G is true, then G is improvable. So what does this tell you? If G is true but not provable, what do you know?
You shouldn't be able to show that G is true?
Suppose it is. This is a difficult meta thinking here. I'll just tell you. Then Principia Mathematica is incomplete. There exists a true but unprovable statement. So G is true, but there is not a demonstration that G is true. That means Principia Mathematica is incomplete. Again, completeness asserts that everything that is true has a proof that it is true. Yet, if G is true, then it is not provable. So there is no proof of G, yet G is true. So if G was true, we are in an incomplete system. Okay, but it's not necessarily the case that G is true. Because if G is not true, G is false. But if G is false, we know that the negation of G is true. Now, what is the negation of G? G is this, so what we could say is there does not exist P such that P demonstrates G. We apply double negation. This just tells us that there exists a P such that P demonstrates G. Right? What does this say? There is a proof of G. So if G is false, the negation of G is true. And we know the negation of G is true. We know that implies that G is provable. And if G is provable, then G is true. What contradicts here? Yeah.
0 is not equal to 1.
Yeah, we are inconsistent, right? G is provable and not provable, violating consistency. So G must be either true or false. If it is true, we are incomplete, and if it is false, we are inconsistent. As long as you have sufficient arithmetic to define these two relations, which apparently only requires addition and multiplication, we'll take a peek at it. You can do this, and therefore you cannot be both consistent and complete because G must be true or false. This is Godel's first incompleteness theorem. Any questions on this? So what he basically showed is that the system that Whitehead and Russell were expecting could not exist. It was impossible, right? This is the first incompleteness theorem. This great program was impossible, that they sought, was completely impossible to find. Question on the first incompleteness theorem.
So he created a proof that proves no system can prove everything.
No system of sufficient arithmetic, and when you get meta, you have to be a little precise. No system of sufficient arithmetic can be both consistent and incomplete. Now it's called the incompleteness theorem. It's called the incompleteness theorem because we want consistency as a bare minimum property. We require consistency, right? So the second case where G is inconsistent is like a horrible scenario. So we would rather have an incomplete but consistent system. So we usually just say G is true. G is false means everything is both true and false. So in some sense, you actually do get completeness if you are inconsistent. But we don't, who cares, right? Inconsistency, the notion of truth is destroyed. So in fact, we don't even, sometimes if you're, an inconsistent system sometimes is not allowed to be defined. So like, you must be consistent, so it must be the case that G is true. That's usually how this is taken. So the system that Russell and Whitehead were looking for could be constructed, but it would never be demonstrably so that they had the right idea, right? Then von Neumann, who I think was in that recent movie about Oppenheimer, he was everywhere. He came up to Godel at this table, and he was the first one to really realize what was going on. And he immediately derived, and Godel as well, what's Godel's second incompleteness theorem. Which is not only were the proofs that Russell and Whitehead were looking for, that consistency was provable, but it was impossible to prove the consistency. No axiomatic system can prove its own consistency if it has sufficient arithmetic. Consistency proofs do exist, but they exist for toy systems. First four axioms of Euclid's elements are consistent. Things like this. It's like you prove consistency, but it appears that you need consistency, you need a system that is stronger, things from stronger math to prove consistency of things that are weaker. That appears to be the case. Now, if you make Principia Mathematica or any such system as strong as possible, it would appear that you are looking for a proof that Principia Mathematica can prove the consistency of Principia Mathematica, if it is the case that Principia Mathematica ought to encode all possible reasoning. So this is what you're searching for. What Godel asserts is this cannot be shown. No axiomatic system of sufficient arithmetic can prove its own consistency. So not only did he say that what Russell and Whitehead were looking for was false, he said that you could actually prove that you could never prove such a thing could happen. He's basically saying Russell, this is the theorem that, another way to state this theorem is that Russell is a loser, because you spent 12 years searching for something that provably could not ever happen or exist, right? Here's how the argument of the second incompleteness theorem goes. Formalize the first theorem in Principia Mathematica. So carefully look, he does this construction very carefully, and note that the proof of the first incompleteness theorem can be done in Principia Mathematica. So first you formalize the proof in Principia Mathematica. You can define the consistency of Principia Mathematica to be a statement of the form like there does not exist P. There does not exist some P such that P demonstrates 0 equals 1, right? If there is no proof of 0 equals 1, the system is consistent. So this is not impossible to define in the well-formed formulas. You can define consistency of Principia Mathematica. Now assume, once you formalize the first theorem in Principia Mathematica, what you're really saying is that Principia Mathematica can prove that what you do is you should take the assumption to the contrary in the first proof. Well, let me say it this way. Assume to the contrary that Principia Mathematica does in fact prove the consistency of Principia Mathematica. Okay? After you formalize the first proof in Principia Mathematica, you know that This proof can be done in Principia Mathematica. What you do is you replace this assumption to the contrary of consistency and completeness with the proof of Principia Mathematica. So what this says is that you also know that Principia Mathematica proves that the consistency of Principia Mathematica implies the resultant of this proof, which is G. Sorry. Right? So if Principia Mathematica can prove the consistency of Principia Mathematica, then Principia Mathematica proves the consistency implies G. Because you formalize the first proof. Together, these combine to say that Principia Mathematica can prove G. Okay? So, if we know that G is provable, if G is provable, G is true. So G is not provable. So G is provable and not provable. Violating consistency. So, in essence, if there exists a proof of consistency, you're inconsistent, as long as you have this sufficient arithmetic. So if you can prove consistency, you're inconsistent. Contradiction. You cannot prove consistency. So this is essentially saying no axiomatic system capable of such sufficient arithmetic can prove its own consistency. This proof especially, any question on the second incompleteness theorem? The first incompleteness theorem is what kind of proof?
Constructive?
Yes, we do construct a G, but I'm looking for a buzzword.
Contradiction?
The word I'm looking for, I guess, is diagonalization. This is also a self-referential diagonalization. It's just a more elaborate version than Russell's construction, but it is no different in some sense. Russell constructs a sentence that says, I am not true. Godel constructs a sentence that says, I am not provable. What really is the difference there, except this slightly more elaborative thing, right? Now, what does this really mean for logic? It means that the hope for the logicians is basically dead. It's like logic can never be strong and perfect, and everything we're working with is quite insane. I'll tell you one more fun fact. No, I'll tell you this one later. Let's just do the book. So two quick things I'll show you is Godel's original proof. This is a book of old papers on the topic, and the first paper here is Godel's proof. So what he does here is he defines a sequence of relations and predicates, and then he goes through these 42 formulae. We talked about GL, we talked about length. This is a concatenation operation he defines, and look, it's like 3 lines long. This concatenates the two formulas. This is the way you turn a symbol into a string, essentially. And then this is how you define parentheses. You just put the parentheses in front, concatenate it with X, concatenate with the close parenthesis. Then he defines variables, negations. Look, he just puts the negation symbol in front of the formula, like this. If you concatenate a negation in the front of the formula, I mean, that's all negation is. He defines these axioms, these types. Here's the axioms. Here's more of it. So he goes through this very, very long and constructive argument. It's very, very difficult. But he's careful to make sure two things. One, the proof can be formalized in Principia. And two, there are no intuitionistic objections. He's very careful to even make sure that every quantifier is bounded, right? One of the last formula here is called BU, which is German for proof or something, I don't know, or demonstrate. There exists Y such that Y proves X is basically what he's saying. X is provable. And this is a little old school, but this is basically what we did, right? And then from here he continues the argument. What's important here is these formulas that we're not going to go through at all because this is terrible. But he invents a programming language basically to hack it. He has to reinvent basic operations that we all know already. It's a terrible thing he has to do, but it's highly creative, and that's why he gets a lot of credit. And people look to him for such a reason. The numbering trick is ahead of its time by over like a millennia or something, right? No, a decade, century, right? Not a millennia. We're back to Logicomics, Papa Dimitriou, and so on. Where we left off was that Russell had just proven that Whitehead's system was inconsistent, and so now what happens is that Principia, these guys, Russell and Whitehead are discussing how can they fix this, and they conjecture about the theory of types, and here it's presented as a kind of caste system, where objects of one type can only reference those less than it. So you create a hierarchy of people who to be shaved. This appears to work on the surface. Then these intelligent guys, Whitehead starts not paying rent, and he moves in with, Russell moves in with Whitehead, doesn't pay rent, sleeps with his wife. 12 years in his house, there's a bunch of drama, whatever. They're trying to do it, Okay, let's skip that. Oh, here's Kurt Godel as a baby. That's baby Godel. No one cares. Oh, Wittgenstein makes an appearance as World War I is happening. Yeah, everything's bad. Everything sucks. Okay, there we go. Hold on, let's see. Okay, here we go. So, yes. At this point, I return to logic. For while I was experimenting with education, logicians, based on our Principia, reached the apex of the struggle towards my youthful dream, to build mathematics on absolute certainty, to place the lowest of beastly things on granite foundations. Yes, and without the abstract language of the Principia, this would have been a pipe dream, though I still felt personally that I had failed. True to the spirit of his Paris talk of 1900 that had also inspired we so much, David Hilbert continued to preach as the struggle's high priest. He spread his message by every means available, including the newest technology of the radio. With the tools of new logic, we shall at last cement the cornerstone of our science, the provability of every mathematical statement or its negation. Never for us the pessimistic ignoramus. Our battle cry is never ignorambis. We must know, we shall know. His message had inspired, among others, a recent acquaintance of mine, which is to be a speaker at the next logical conference, held right inside the lair of the Vienna Circle. So here's Godel, he's reading the three volumes of Principia Mathematica. He's only one of 5 people in the world that bothered to actually read the book. Hello, Schlick, have you discovered Wittgenstein's true age yet? Haha. He returns to Vienna soon. We shall observe empirically. I present a brilliant young colleague, her Dr. von Neumann, and honor her, Professor. Say, I wonder how you chaps can like me and Wittgenstein, especially given our difference on mathematics. Maybe the next speaker will settle your matters in your favor. Rumor has it he solved Hilbert's second problem, the consistency and completeness of arithmetic, and thus all of mathematics. My goodness gracious. It's hard to exaggerate the feeling of excited anticipation as Kurt Godel began his talk. Her professors, Hilbert and Russell, distinguished colleagues, I will speak to you of, he's a Platonist, light years from Wittgenstein. My research in the provability and propositions of arithmetic. Like you, he believes logic to be an image of the highest form of truth. The powerful methods of Principia now allow us for the first time in history to speak of a correctly formulated question in theories of mathematics, and thus further to ask, is a correctly formulated mathematical question necessarily answerable? And then Hilbert's there with his little hat, he says, obviously. In other words, is every mathematical statement provable, either the statement itself or if it states something false, its opposite? It is to this most fundamental question that I have found the answer, which is no. Or to put it differently, there will always be unanswerable questions. Her doctor, sure you mean unanswered questions, yeah? No. Since the scope of truth is infinite, obviously there will always be unanswered questions. What I mean precisely now is this, unanswerable. What I have proved in essence is that arithmetic, and thus any system based on it, is of necessity incomplete. And in Godel's lecture, the audience had expected the confirmation of their cherished vision. So, and here he goes, Gen R is not provable, for if it were, there would be an n such that, and you can see some of the notation he uses, there's a 17 here, it's a little old school. They got something completely different. It's all over. It's all over. Von Neumann's comment perfectly sums up the essence of Godel's proof. I know it may be hard for laypersons to understand, but for a lot of very intelligent people, the incompleteness theorem meant the end of a dream. The dream had theological ancestry. Its credo had been written in Greek 2.5 millennia ago. And now suddenly the rug had been pulled from the feet of the dreamers. Her professor, would you like to take us to your hotel? That is the beauty and the terror of mathematics. There is no getting around a proof, even if it proves that something is unprovable. So this was the end of an era that they sought themselves as extensions of Euclid. They thought these guys to be an extension of the axiomatic method, which had foundations in religion and the first Greek demonstrations from geometry. This was the way rationality had progressed from the year literally 300 BC. And it was the dominant strategy of thinking, and these guys thought themselves as champions of this. They were formalizing it, but they didn't. This simple argument basically blows the whole thing apart. It could never be finished in some sense. The project is dead. It's over. Any questions? All right.